In this video, we are going to be looking at how to calculate the amount of reactive power you need in order to correct the power factor at a specific site. We are going to be doing the calculation, and then we are going to be looking at how to do the calculation by using a power factor table. Where I would like to start with this presentation is by just looking at what power factor is, what a good power factor is, and kind of being able to identify what a bad power factor is. On the screen, you'll be able to see we've got a chemical plant on the left-hand axis. We have an orange arrow, and the arrow shows us the kilowatt for this particular site. If we were to look at the legend, we'll see that the legend shows the summed power in kilowatt. We quickly try to understand what it is we are looking at and what it is we are seeing. This is a one-day cycle. On the left-hand side, we can see the y-axis starting at -2 and ending at 37. If we pick a specific time, we'll see that at 10:30 on the morning, our load was 21 kilowatt. If I add reactive power, reactive is the green line, and if I add kVA, kVA is the blue line. I'm going to take the green line away again so that we can look at kVA. If we take the power value away, which is the red line, we'll see that the blue and the red sits at more or less the same place. We see the kilowatt and the kVA sitting at more or less the same place. This is ideal for any kind of three-phase installation. I'm going to add the power factor. And what the power factor has done is it has added an additional black line to the list. So what I'm going to do is I'm going to remove the kilowatt and the kVA from the graph so that we can just focus on the black line. When we look at the black line, where we are going to be reading the black line would be on the right-hand side of the graph. And we'll see that the values we have over here varies between about 1 and 0.96. Now, when you have a pretty good power factor of 1 is what we call unity. We want to try and get the power factor as close as possible to 1. In this particular graph, we can see that the power factor sits at about 0.99, with the power factor sitting in, with the bulk of the power factor sitting in that range over there. So with the bulk of the power factor sitting in that range over there, if we look at the right-hand side, we'll see that where it's represented on the graph itself sits at about 0.99. That is extremely close to 1, and that is an amazing power factor. This particular site has an active power filter installed, and it manages the power filter, it manages the power factor dynamically. When we look at how the power factor is being managed, if we take that section over there, what you'll see is that the power factor happens in steps. There's a step over there. There's another step over there. Then there's one more step over there. There's another step more or less there. And then there's another step there. So the power factor is implemented on this particular site in very small increments over a fairly short period of time. So what we've got with this particular active filter is that the active filter is continuously measuring and adjusting, measuring and adjusting, measuring and adjusting. And those adjustments is what we see in those steps that are reflected on this particular graph. So now we've got the reactive power, we've got the kilowatt, and we've got the kVA. The power factor, the kilowatt, and the kVA can be represented by a triangle. And if we look at what we've got, or what we had on the graph, we had about 20 kilowatts. And that line I'm going to draw down to there. And then if I activate the reactive power, we'll see that at that time, the reactive power, so the reactive power is measured in kVAr. So kVAr, which is kVA reactive. And when the load was 20 kilowatts, the reactive power was about 2.7 kVAr. And the kVA was just a little above it. kVA came in at about 21 point, where I'm reading this is in line with the line going down, so I'm reading it there. And that to me looks like it's 21.5. So we've got 21.5 kVA, and we had about 2.7 kVAr. When we look at an installation where the power factor is not good, there will be more reactive power. And because the reactive power component is bigger, that line is going to be longer, which means that our kVA is going to be higher. So we could be drawing 20 kilowatt, and we could end up drawing 40 kVA if we had an additional reactive power component on that side of the graph. This triangle we've got over here can be calculated by using the Pythagorean equation. If we have any one of these three and we have the power factor, we would be able to calculate any of the other values on the graph. This is a good power factor. Let's quickly have a look at a bad power factor. When we look at this graph, you'll see exactly the same, the lines have the same colors. So the kilowatts represented by the red line, if we look at that spot over there, we'll see that that was 7.5 kilowatts. If we bring the kVA into the equation, you'll see that now the kilowatts and the kVA is very far removed. So we have the kilowatts at the bottom and the kVA right at the top. Look at the amount of kVA in this particular graph. Let's change it to be the same color as I'm going to make it slightly lighter. So in this particular graph, we are sitting with a 7.5 kilowatt load, but we are sitting with a significantly higher kVA. In our second graph, we had a 7.5 kilowatt load, but in the second graph, our kVA was significantly higher. Our kVA was 47.5 kVA. You guys see, with the low load that we have and the massive kVA value we have over there, the only reason for this could be that we must have a very big reactive power component. This power component over here is responsible for the extremely high power factor and the extremely high apparent power that we are busy drawing on the site. So we've got a 47.5 kVA load on the transformer, even though the actual load of what we are using on site is only 7.5 kilowatts. What we want to do is we want to be able to correct this so that we can bring the reactive power down and we can bring that value down. We want to be able to optimize the site and to reduce the losses in this particular installation by addressing the reactive power component on the particular site. I want to jump back into, so we've got a low load, we've got a high apparent power, the reactive power component. You'll see that the reactive power component is 47 kVAr. The component we have over here is also 47 kVAr. So our reactive component is extremely large in comparison to the first graph we had a look at, where the power factor was fine and we had a very low reactive power component. If we go back to our graphs, the first graph we had a look at had an amazing power factor. If we look at the right-hand side over here, the y-axis on the right-hand side, we'll see that our power factor sits at 0.9. If we were to look at the other graph, we'll see that our power factor sits at 0.1. It varies between about 0.1 and 0.2. This must be one of the worst installations I have ever measured in terms of power factor. So if I look at where the power factor sits on average, it's somewhere between about 0.25 and 0.1, which means that just about all of the power on the site is reactive, and a very small component of the power on this particular site is being used for useful work. If we look at the other graph, the other graph's power factor sits there. Sits about there, 0.99. The ideal place for power factor is roughly where it was on the other graph, which is 0.99. So the ideal place for power factor sits there. This particular wine farm is nowhere near ideal. Unfortunately, in order to calculate what you need to offset with power factor correction equipment, you have to have the right loggers and you have to have the right equipment that would be able to measure and give you the correct information. So if you have the load and you have the power factor, so if you have a load of 20 kilowatts and you have a power factor of 0.6, for example, if you know that and you know that, you'd be able to calculate the kVA, you'd be able to calculate the kVAr, and you would be able to calculate how much capacitance you need in order to inject into this installation to correct the reactive power to where it's supposed to be. The way we do this, so if you have a 20 kilowatt load and a power factor of 0.6, your kVA is always going to be higher than what your kilowatts are. So in order to go from kilowatt to kVA, we're going to take that value and divide it by the 0.6. So 20 divided by 0.6 equals 33.33. That means that we've got a 33.3 kVA in our system, or 33.3 kVA load on the transformer. We've got this value and we've got that value, so we would now be able to calculate the kVAr in the installation. And the way we calculate the kVAr in the calculation is by using the Pythagorean formula. And that is equal to 33.3 squared minus 20 squared. And that would be equal to 33.3 squared minus 20 squared equals 708.89, and then we can get the square root of that is equal to 26.62. And that is equal to 26.62, and that is equal to 26.62 kVAr. So if we have a 20 kilowatt load, we have a power factor of 0.6. We have 33.3 kVA of apparent power, and we have 26 kVAr of reactive power. Now, the way we would go about calculating how much we need in order to correct this with a capacitor bank, we would first of all determine what we want the power factor to be. So if we wanted the power factor, and I'm going to do this in red, 0.6 is on site. That's the power factor on site. And 0.9 is the target that we would want to achieve. So what we would do is we are going to redo this entire calculation just using the target power factor as what it is we're going to be aiming to achieve. So to have a 0.9 target would mean that we would take the 20, we would divide that. So 20 divided by 0.9, 20 divided by 0.9 is equal to 22.2 kVA. That is what we would like to achieve. So 22.2 kVA is the target. That means that we have to now understand what the reactive power has to be in order to have a 22.2 kVA targeted apparent power. We'll do exactly the same calculation where we'll take the square root of 22.2 squared minus 20 squared. So we'll go 22.2 squared minus 20 squared equals 93.83. We'll get the square root of that, and that would be a value of 9.68. So 9.68 kVAr is the targeted reactive power that we want. In order to understand how much capacitors or capacitance we require on site, we would deduct that value from this value. So we would go 26.62 minus 9.68 kVAr, 26.62 minus 9.68 is equal to 16.94 kVAr needs to be injected in the form of capacitance into the electrical network in order to achieve a 9.68 kVAr. And once we've achieved this, our apparent power will be reduced to 22.2 kVA. What I would like to do is we've got a power factor correction table to make things easier. And if we look at the power factor correction table, our power factor correction table is over here. And how the power factor correction table works is that you look at your measured power factor and you identify your target power factor. So we've got the measured power factor. 0.6 is what we've measured. 0.9 is what we'd like to achieve. So our factor is 0.849. If you don't want to do all of these calculations, what you can do is you can use a power factor correction table. You can take the kilowatts over there and multiply it by 0.849 because that's the value that is in the power factor correction table. And we go 20 times 0.849. That equals 16.98. And that is equal to 16.98 kVAr, which is the same as the value we have allocated or calculated using the long method. And that brings us to the end of this particular video. The aim of this particular video was to understand how much capacitance we need to inject into this electrical network to get the apparent power down from 33 to 22 kVA. Using the long method, we calculated 16.9 kVAr, and using the power factor correction table, we calculated 16.9 kVAr. Now, before you run out to go and get capacitors to cover 16.9 kVAr, you've got to make sure before you do your installation that your cabinet is sized correctly, that the power factor correction equipment has been installed in the right place in your electrical network, and then also that you have some filters installed that would be able to protect your capacitors against resonance and harmonics. But that we'll cover in a different video. Thank you very much for watching. If you enjoyed the video, like and subscribe. Alternatively, you can always subscribe to one of our courses that we offer. We have courses that are slightly longer and more intense. Guys, thanks for watching. Looking forward to seeing you again in one of the next videos.